f dash of x equals the limit as h approaches 0. It's important to always put this limit term in there unless you no longer want it. We'll look at that in a second. So 2 multiplied by x plus h all squared, which is the function of x plus h, minus f of x, which is just 2x squared, all divided by h. We then expand the brackets on the top line, cancel out the plus 2x squared minus 2x squared. We then factorise, taking h out as a common factor on the top line, cancel out the h on the top line and the bottom line to give a final function as f dash of x equals the limit as h approaches 0 of 4x plus 2h. Now we no longer have a division by 0 situation if h approaches 0 as we would have in the original version. So we end up with the ability to substitute in h equals 0 as 4x plus 2h approaches 4x as h approaches 0. So our slope function, which gives the slope at any point, is in fact 4x. Now we go back to the original question. It doesn't ask for the slope function, it asks for the slope at a particular point. So we need to take that point of x equals 2, substitute it into the slope function to give ourselves the slope at x equals 2 equals 4 times 2, which is 8. Let's try a slightly more complex example. Here we have f of x equals x to the minus 2, and again we need to find the slope at a particular point. So let's rewrite that in a form we can use more easily, which is f of x is 1 on x squared. We then substitute into the original formula. Now in this case we need to make these two fractions over a common denominator. That common denominator is the two terms multiplied together. Here we have both fractions over a common denominator collected into a single fraction. Now we take these two terms here, we're dividing by one term and then dividing by another. We can actually put those into a shared denominator, which is the two terms multiplied by each other, as shown here. We can then expand the brackets on the top line. Don't touch the brackets on the bottom line, only the top line. We expand those brackets, multiply through by the minus 1 here, cancel out plus x squared and minus x squared. We then are able to take h out as a common factor from the remaining terms, cancel that out on the top and the bottom line. We now have a situation where we can substitute in h equals 0 without giving ourselves a division by 0 situation into this final equation here. As h approaches 0, minus 2x minus h approaches minus 2x, and x plus h approaches x. So we end up with a final function here. Note the limit term here is gone because we're no longer after the limit because there's no more h's involved. We then collect the x squareds on the bottom line, cancel out 1x on the top and the bottom line to give a final slope function of minus 2 divided by x cubed. Again, we need to find the slope at a particular point, so we substitute in that x value and end up with a final slope of minus 1 on 32. Now let's try a slightly more complex version of the same type of equation. Again, we substitute the equation into the original formula, place it over a common denominator for the top line, collect it into a single fraction, collect the two denominators into a single denominator, expand the brackets on the top line, cancel out the common terms, so plus 2x squared minus 2x squared and minus 18 plus 18. Bring h as a common factor for the remaining terms, cancel that out top and bottom line. We then end up with a situation where we can just substitute in h equals 0 without getting a division by 0 situation. So we end up with a final slope function. Again, the limit term here is gone because this is the limit of that. Collect the x squared minus 9's on the bottom line to get minus 4x divided by x squared minus 9 all squared. Again, going back to the original question, we weren't asked for the slope function, we were asked for the slope at a particular point. So we substitute in that x value, run through the numbers, and we end up with the final answer of the slope at x equals 2 equals minus 16 divided by 49. Because minus 16 and 49 have no common factors, we can't simplify any further, and unless asked to do so, we wouldn't go for a decimal approximation. Let's go try an example with a fractional index. In this case we have 4 multiplied by the square root of x, which is the same thing as 4 multiplied by x to the power of a half. And again we need to find the slope at a particular point. So we start by substituting in the function into the original formula. Now in this case we need to multiply the top line by its difference of perfect squares conjugate. So we have the difference of two terms, we need to multiply it by the sum of those same two terms. Now in order to not change the value, we need to make sure that that's being multiplied by 1, which is that the difference of perfect squares conjugate divided by itself, because anything divided by itself is 1. So we end up with a top line which is the difference of these two terms squared. So this term squared is there, this term squared is there, and the bottom line is simply h multiplied by that bottom line, remembering that that bottom line there needs to be placed in brackets in order that h is multiplied by all of it, not just the first term. So here are the brackets right there. We then expand the brackets on the top line only, don't touch the brackets on the bottom line, cancel out plus 16x and minus 16x, cancel out the h on the top line and the bottom line, and giving ourselves a final equation shown here. Now we have a bottom line without h, so we can substitute in h equals 0 without getting to a division by 0 situation. So we end up with f dash of x is 16 divided by 4 root x plus 4 root x, collect the like terms on the bottom line, cancel out, giving ourselves a final slope function, and again we need to substitute in the original value of x to get a particular slope at a particular point. So in this case the slope at x equals 4 equals 2 divided by root 4, which is 2 divided by 2, so it's 1. Now, due to popular request, I've got one here that combines the negative and fractional indices. The algebra gets quite ugly, but let's go through it anyway. So in this case we have 2 divided by the square root of x, which is 2 multiplied by x to the negative a half. And we need to find the slope at the slope at x equals 27 by using first principles. Again, we substitute in the function into the original formula, multiplied by the difference of perfect squares conjugate. We end up with the difference of perfect squares on the top line, and again h multiplied by that conjugate on the bottom line. As we can see here, we've got fractions on the top line and the bottom line, so the algebra does get quite messy. We then need to collect the top line over a common denominator. Move that common denominator down to the bottom line by multiplying it through by the bottom line. So x multiplied by x plus h is down here, multiplied by h. So basically, just for convenience, we've placed it between the h and the fractional term on the bottom line. We then cancel out the 4x and minus 4x on the top line, giving ourselves h on the top line and the bottom line, which we can then also cancel out. We then again have a situation where we can substitute in h equals 0 without getting to a division by 0 situation, which is here. We then substitute in h equals 0 everywhere h appears, so all these terms tend towards x and x, where it was previously x plus h, and notice the limit term is now gone but was previously there for every version before that. We then collect like terms, cancel out, and we end up with a final version of the slope function, which is minus 1 on x root x, which is also minus 1 divided by x to the power of 3 on 2. Again, we're going back to the original version, original question, which asks for the slope at a particular point, that point being x equals 27. There's more versions of the slope function. And once we substitute in x equals 27, x to the minus 2/3 equals minus 27 to the power of minus 2/3, which is minus 1 divided by 9. Now we have some practice questions for you to do. You'll need to pause the video while you do them, as the answers follow. And now for the answers. Note that some of these answers are for slopes at a particular point and some are for slopes at any value of x, as was requested specifically in each of the questions. That's all for this tutorial. Thank you very much for watching the ASMS tutorial on differentiation by first principles, worked examples.